Well, thank you for that fantastic introduction, Jonathan. And it actually really is a pleasure to speak here again at the end of the year. We had the first WebAssembly SF at the Mozilla office in January, and so it's nice to get a chance to wrap out the year with you all. So hi, I am Lin Clark, and I make code cartoons. I'm also on the developer technologies team at Mozilla, so we work on things like the Rust programming language and also WebAssemblies outside the browser use cases. And fortunately, many of the folks working on those outside the browser use cases are here today. We're here in SF this week to collaborate because we made this announcement last month, which you may have seen. It's a cross-industry partnership with Fastly, Intel, and Red Hat, and we're bringing in more partners as well, and we call this the Bytecode Alliance. We're coming together to forge WebAssemblies outside the browser future by collaborating on implementing standards and proposing new ones. And that phrase there, the implementing standards part, is pretty important, and I'll explain more about what that means later. But first, I want to talk about why we're coming together. And that's because WebAssembly has already started moving outside of the web. The portability and the scalability that WebAssembly provides, the fact that with WebAssembly it's possible to run the same binary across different devices at near native performance, that's really attractive for a lot of use cases where you would usually write native code. But as people are bringing WebAssembly outside of the web, they're leaving the browser sandbox behind. And if that becomes the best practice, then we lose one of the major benefits of WebAssembly, its security. We really shouldn't give up on WebAssembly's security because WebAssembly gives us a chance to solve one of tomorrow's biggest security challenges. And this is one that comes from the radical change that we've seen in software development over the past 20 years. If you look at old issues of Computer World, you'll actually see articles about companies having a really hard time getting developers to reuse code, from 2003. But now we're building massively modular applications where 80% of the code comes from package registries like npm and PyPI and crates.io. Even C++ is moving towards enabling an ecosystem of these composable modules. Now, making use of these ecosystems, that isn't bad. In fact, it's good. The problem is that the current software architectures weren't built to make it safe to reuse this code. And bad guys are taking advantage of this. And they're doing that at dramatically increasing rates. What the bad guys are exploiting here is that we've gotten our users to trust us. When the user starts your application, it's like the user's giving your code the keys to their house. They're saying, I trust you to your application. But then you invite all of your dependencies, giving each one of them a full set of house keys to that house. And these dependencies are written by people you don't know and have no reason to trust. And more than this, it's not even just your own dependencies that come along for the ride. It's also any modules that they depend on, so the indirect dependencies. Now, what do these developers get access to? They get access to the resources on the machine, so things like files and memory. And they also get access to the APIs and syscalls, these tools that they can use to do things with those resources. So this means that these modules can do a lot of damage. They have the access to do a lot of damage. This could either be on purpose, as with malicious code, or completely accidentally, as with vulnerable code. So let's look at how these attacks work. Malicious code is written by the attacker themselves. Attackers often use social engineering to get their package into an application. So they create a package that has useful features, and then they sneak in some malicious code with those useful features. Once the code is in an app, that's when they start doing that. That's when they start adding that malicious code that attacks the user. And this is how an attacker stole $1.5 million worth of cryptocurrency from users, and they almost got $13 million more. So on day 0, the attacker published a module to npm, and this module was called Electron Native Notify. Now, it seemed useful. It helped Electron apps fire off native notifications in a way that worked across platforms. And it didn't have any malicious code in it yet. Now, to pull off this heist, the attacker has to get this module into the cryptocurrency app. So the attacker decided to target a dependency in that app, in an application that users use to manage their cryptocurrency, the Agama wallet. So the attacker posted a PR that added this module to a dependency of the Agama wallet, EasyDex GUI. On day 17, the attacker added the malicious payload to their module, so this is to Electron native notify. And somewhere between day 41 and day 66, the Agama wallet actually updated their dependencies, and so they pulled in the new version of EasyDex GUI and the new version of Electron native notify with it. So at this point, the malicious code started sending seeds, which are the username and password combinations for the wallets, to a server. And then the attacker could use these seeds to empty the user's wallets. On day 90, a user, not part of this ecosystem, of the cryptocurrency ecosystem, but just a user of Electron native notified NPM and said, this module is doing some weird stuff. And so NPM notified the cryptocurrency platform, which moved funds from vulnerable wallets to a secure one. But unfortunately, the attacker was already able to collect $1.5 million worth of that currency. Let's look at what access this malicious code needed in order to pull off this attack. So it needed the seed, that username password combo. And to do this, it got access to the memory that was holding that variable. And then it needed to send the seed to a server. So for this, it needed access to a socket and access to an API or syscall for opening that socket. So that's how a malicious attacker can pull off one of these attacks. And these attacks are on the rise as more and more attackers realize how vulnerable our systems of trust leave us. So for example, the number of malicious modules published to NPM more than doubled between 2017 and 2019. And Adam Baldwin, NPM's Vice President of Security, points out that these attacks are getting more and more serious. So he says, in 2019, we're seeing more financially motivated attacks. Early attacks were focused on shenanigans, deleting files and trying to steal some credentials. Real basic attacks, kind of smash and grab style. Now end users are the targets. And the attackers are trying hard to be patient, to be sneaky, to really have a well-planned out attack. Now let's look at how exploiting a vulnerability works. So vulnerabilities are different than malicious code. The module maintainer isn't actually trying to do anything wrong. The module maintainer just has a bug in their code. But attackers can use that bug to trick the code into doing something that it shouldn't do. So for an example of this, let's look at zip-slip. This is such a tongue twister. Zip-slip is a vulnerability found in modules in many ecosystems. So it's in JavaScript, Java, .NET, Go, Ruby, C++, Python, and even more. And it's affected thousands of projects, including ones from HP and Amazon, Apache, Pivotal, and others. If a module has this vulnerability, attackers can use it to replace files anywhere in the file system. So for example, the attacker could use it to replace JS files in the no modules directory. And then when that JS file is required, the attacker's code will run. So how does this work? The attacker creates a file on their own machine and zips it up, and they give that file a file name that includes a relative file path that escapes up to a higher level directory. Now when the vulnerable code unzips it, it doesn't sanitize the file name and just calls write with that, that write syscall with the relative path. So it places that file wherever the attacker wanted it to go in the file system. So what access did the vulnerable code need for the attacker to be able to pull this off? It needed access to the directory with those sensitive files, so in that example, the node modules directory. And it also needed access to the write system call. Just as with malicious code, vulnerabilities like these are on the rise as well. So SNCC, which is a security company, reports that there's been an 88% increase in the last 2 years in these kinds of vulnerabilities across ecosystems. Now with these risks, you would think that patching these vulnerabilities would be a really high priority. But as Nick found, only 59% of packages have known fixes for the disclosed vulnerabilities, because many maintainers don't have the time or security know-how to fix these vulnerabilities. And this leads to widespread vulnerability across the ecosystem, as these vulnerable modules are depended on by other modules. So for example, a study of NPM found that up to 40% of packages depend on code with at least one publicly known vulnerability. So how can you protect your users against these threats in today's software ecosystems? Well, you can run scanners that detect fishy coding patterns in your code or the code of your dependencies, but there are many, many things that these can't catch. You can subscribe to a monitoring service that alerts you when a vulnerability is found in one of your dependencies. But this only works if that vulnerability has been found. And even once the vulnerability has been found, there's a good chance the maintainer won't be able to fix it quickly. As Nick found, for the top 6 packages in the NPM ecosystem, the median time to fix was 2.5 years. You could try and do manual code review. So whenever there's an update in a dependency, you'd review the changed lines of code. But if you have hundreds of modules in your dependency tree, that can easily be 100,000 lines of code to review every few weeks. You could pin your dependencies so that malicious code can't get in until you've had a chance to review it. But then fixes for vulnerabilities would be stalled, leaving your app vulnerable to those things longer. So this all makes for kind of a no-win situation, which could make you want to throw up your hands in disgust and just hope for the best. But as an industry, we simply can't do that. There's too much at stake for our users. So there is something in common with all of these approaches. All of them try to catch malicious code and vulnerable code after it's already been introduced into the system. But what if we look at this a different way? Part of the problem here was the access that these modules had. What if you took away that access? So we faced this kind of challenge as an industry before, just at a different granularity. When you have 2 programs running on a computer at the same time, how do you know that one of these programs won't mess with another program? Do you have to trust the programs to behave? No, you don't, because the protection is built into the operating system. Now, the tool that operating systems use to protect programs from each other is the process. When you start a program, the operating system fires up a new process. And each process gets its own chunk of memory to use, and it can't access the memory in other processes. So if it wants to get data from one of the other processes, it has to ask. And then that data is sent across the process boundary. So this makes sure that each program is in control of its own memory. This memory isolation does make it safer to run 2 programs at the same time, but it isn't perfect security. A malicious program can still mess with other resources, like files in the file system. So VMs and containers were developed to fix these kinds of problems. They ensure that something running inside of them can't access the file system of another. And with sandboxing, it's possible to take away the access to APIs and syscalls. So could we put each one of these packages into their own little isolated unit, its own little sandboxed process? Well, that would solve our problem, but it would also introduce a new problem. All of these technologies are relatively heavyweight. If we wrap hundreds of packages into their own sandbox processes, we'd quickly run out of memory. And we'd also make the function calls between the different packages much slower and more complicated. But it turns out that WebAssembly gives us new options. WebAssembly can provide this kind of isolation that makes it safe to run untrusted code. And we can have an architecture that's like Unix's many small processes or like containers and microservices. But this isolation is much lighter weight, and the communication between them isn't much slower than a regular function call. So this means you can use them to wrap single WebAssembly module instances, or a small collection of modules that want to share things like memory among themselves. And with this, you don't have to give up the nice programming language affordances like function signatures and static type checking. So how does this work? What is it about WebAssembly that makes this possible? Well, first, there's the fact that Each WebAssembly module is sandboxed by default. So by default, the module doesn't have access to APIs and system calls. If you want a module to be able to interact with anything outside of the module, you have to explicitly pass in a function that that module can call to interact with the host. Second, there's the memory model. So unlike a normal binary compiled directly to something like x86, a WebAssembly module doesn't have access to all of the memory that's in the process. It only has access to the chunk of memory that's been assigned to it. So this gives us memory isolation between two modules that are running in the same process. And that means that a malicious module can't mess with the memory of its parent module. But then how do we share data from our module? You have to pass it in and out as the values of the function call. And there's a problem here. By default, WebAssembly only has a handful of numeric types. And that means you can only pass single digits across. Here's where the third feature comes in. And we've been talking about this a bit tonight. This is the interface types proposal, which we demoed in August. With interface types, modules can communicate using more complex values, so things like strings and sequences and records and variants and nested combinations of all of these. And that makes it easy for two modules to exchange data, but in a way that's secure and fast. So the WebAssembly engine can do direct copies between the caller and callee's memories without having to serialize and deserialize that data. And this works even if the two modules aren't compiled from the same language. So with all of that, we can isolate the memory between modules without making it too hard to share data. This way, we can ensure that a malicious module can't mess with the memory of other modules in the application. But we don't just need to take precautions around how memory is handled between these different modules, because if the application is going to be able to do anything with that data, it's going to need to call APIs and system calls. And those APIs or system calls might have access to shared resources like the file system. So we need APIs and system calls that actually have the concept of permissions baked into them. And this way we can give different modules different permissions to different resources. This is where the fourth feature comes in, WASI, the WebAssembly System Interface, which we've also been talking about tonight. That gives us a way to isolate these different modules from each other and give them fine-grained permissions to particular parts of the file system and other resources, and also fine-grained permissions for different system calls. So with this, we've taken control of the keys. What's missing? Well, right now, we don't have a way to pass these keys down through the dependency. We need a way for parent modules to give the keys to their dependencies. And this way, they can give their dependencies either the exact same keys that they have, or they can choose which keys they want to give to their dependencies from the set that they have and push those ones down. And then those dependencies can do the same thing for their children all the way down through the tree. That's what we're working on next. In technical terms, we're planning to use a fine-grained form of per-module virtualization. And this is an idea that researchers have demonstrated in research contexts, and we're working on bringing this to WebAssembly. And in particular, Luke Wagner is working on bringing this to WebAssembly. So you should check out the explainer for his linking proposal. Taken all together, these features make it possible for us to have similar isolation to that of a process, but with much lower overhead. This pattern of uses is what we're calling the WebAssembly nanoprocess. It's still just WebAssembly, but it follows a particular pattern. And if we build this pattern into the tools and conventions that we're using, we can make third-party code reuse safe in WebAssembly in a way that it's not in other ecosystems to date. With these foundations in place, developers will be able to build dependency trees of isolated packages, each with their own tiny little nanoprocess around them. So how does this help keep the user safe? Well, in both of these cases, it's the fact that we're following the principle of least authority that's going to keep the user secure. So let's walk through how this helps. In order to carry out an attack, a module often needs access to resources in an API that it wouldn't otherwise have access to. And with our approach, the module has to declare these things. They have to declare what access they need. So this makes it easy to see when a module is asking for something that it shouldn't be. So for example, the wallet stealing module needed access to both the socket pointing to the server and the ability to open a network connection. But this module was just supposed to take in some text that was passed into it and hand it off to the system so that the system could display it. So why would a module like that need to open a network connection to do what it's supposed to do? If Electron native Notify had asked for these permissions from the start, that would have been a serious red flag. So the maintainers of EasyDex GUI probably wouldn't have accepted it into their dependency tree. If the malicious maintainer had tried sometime after it was already in that dependency tree to add those, then it would have been a breaking change. So the module signature would have changed, WebAssembly would have thrown an error, and the module maintainers would have had a chance to make the decision whether or not they wanted to expand the access that this module had. Even if the maintainer of this module were somehow able to trick the maintainers of EasyDex GUI to accept it, they still would have had an extremely hard time getting the seed. And that's because the seed would be in another module's memory. And there are two ways for a module to get access to some other module's memory, and neither of them allow the malicious module to be sneaky about it. So either the module that has the seed exports the seed variable, making it automatically visible to all other modules in the system, or the module that has the seed passes it directly into the malicious module. And both of these seem incredibly unlikely for a variable that is this sensitive. There is unfortunately one less straightforward way that attackers can access another module's memory, and this is through side channel attacks like Spectre. So if you're architecting your code with these, and trying to protect them from these kinds of attacks, from Spectre attacks, using processes now, you may still need to use full operating system processes. Making the shift to nanoprocess here would take careful analysis. But there are lots of situations where timing protection isn't needed, or where people aren't using processes right now because they are too heavyweight. And these are good candidates for nanoprocesses. So how does this protect against attackers exploiting vulnerabilities? Well, just as with malicious modules, it's less likely that a vulnerable module legitimately needs the combination of access rights that the attacker needs in order to pull off their attack. So in the zip slip example, even for legitimate uses, the vulnerable module does not need access to a dangerous syscall, the right syscall, or does need access rather, to the right syscall, which is a dangerous syscall. But it doesn't need access to the node modules directory for any legitimate use. It would only have access to that directory which the parent passes to it. And that would be the directory that the zip files are supposed to go into, a download directory, something like that. That makes it impossible for the vulnerable module to carry out the attacker's wishes, unless the parent knowingly passes a very sensitive directory into the vulnerable module. Now, as noted in that caveat above, it's possible that the application developer would pass a sensitive directory, like the root directory, in, but for that to work, the mistake would have to be made in the top level package, so in the very, very top level. And it can't happen in a transitive dependency. So by making all of that access explicit, it makes it much easier to catch these kinds of sloppy mistakes in your code review. So that's how WebAssembly could solve this problem. But this kind of security guarantee doesn't just fall out from using WebAssembly. As I've mentioned before, this is a pattern of usage. The components that we're building up to build up this pattern, they're all being standardized, but following this pattern is a requirement to use WebAssembly. If we want to have these security properties, we have to follow this pattern. We have to establish these as conventions and bake them into our tools. And that takes some work. As a community, we have a choice. We can choose to fix this growing security issue and make our users secure by default. As we design the pieces of this new ecosystem and how they fit together, we can bake the security into our tools, into the design of those pieces. But if we don't, WebAssembly could make the problem even worse. We know what future we want to see. We want to stand for the user and fix this problem. And it's a problem that's too big to solve alone. That's where the Bytecode Alliance comes in. So what role does the Bytecode Alliance play here? Now, some people have thought we're a new standards organization. That's not the case. All of the standardization of all of these things is still happening in the W3C. And Bytecode Alliance members are playing an active role in the standards, all of the standards that I've mentioned, but the standardization is still happening outside of the Bytecode Alliance itself. What is happening in the Bytecode Alliance is the implementation. We're implementing these standards. We're building runtimes and tooling that follows these standards and follows this pattern. Then people can use these building blocks that we're building to run their own applications, whether on the cloud, natively, on someone's desktop, or even on tiny IoT devices. And we're building these runtimes and this tooling in an opinionated way, one that's secure by default. So they're built around this nanoprocess pattern. With this, developers can be as productive as they are today, using open source the same way that they do today with NPM and PyPI and Crates.io, but without putting their users at risk. So what exactly are we building? So we're building out WebAssembly standalone runtimes that address use cases across the spectrum, from tiny devices up to large data centers. The most general purpose of these is WASMtime. It's a standalone WebAssembly runtime that can be used as a CLI tool or embedded into other systems. And it's very configurable and scalable so that it can serve as the basis for many use case specific runtimes, from small devices all the way up to the data centers. Lucet is an example of a use case specific runtime, ideal for CDNs and edge compute, using AOT compilation and other techniques to provide low latency and high concurrency. And we're actually refactoring that to use WASMtime as its core. So it's being built up on top of WASMtime in this refactoring. And then there's also the WebAssembly micro runtime, which is another use case specific runtime. It's ideal for small embedded devices that have extremely limited resources and ones that Rust can't currently target. It provides a small footprint and uses an interpreter to keep memory overhead low. We're also building out reusable components that can be used in these runtimes. So CraneLift is emerging as a state-of-the-art code generator. It's designed to generate optimized machine code very quickly because it parallelizes the compilation on a function-by-function level. And WASI Common is a standalone implementation of the WebAssembly system interface that runtimes can use. We also have quite a few projects which help with building out language tool chains for people that are producing WebAssembly modules. And we have a lot of these, so just a few highlights. Cargo WASI, which Alex has worked on, is a lightweight cargo subcommand that compiles Rust code to target WebAssembly and WASI. WAT and WASM parser parse WebAssembly. So WAT parses the text format, and WASM parser is an event-driven library for parsing the binary format. And WASM interface types is a Rust toolkit for working with interface types. So these are a few of the things that we're working on, and we expect this set of projects to expand as we grow the Alliance. And our members are also leading the WASI standards effort itself and the Rust to WebAssembly toolchain. Now we're doing all of this because to us it's really important that WebAssembly achieves its potential. As WebAssembly's co-creator Luke Wagner said, this is a unique moment in time at the dawn of a new technology, where we have the opportunity to fix what's broken and build new secure by default foundations for native development that are portable and scalable. But we need to take deliberate cross-industry action to ensure that this happens in the right way. And we hope that you'll all join us in that. So now, if you want to chat more about the Bytecode Alliance, we fortunately do have a lot of the members here tonight. So let's open it up to questions.